Hello, friends. Greetings to all of you once again, and I welcome you to this lecture on bearing capacity of soils. In my earlier lectures, we have covered a few things, which quick recap of the same, because before discussing today the Prandtl's method and the Terzaghi's method for finding out the bearing capacity of soils, it is very pertinent and important to understand some of the terms what we have discussed in my last lecture. You see the safe bearing capacity of soil according to the Indian Standard Code 6403-1981, the maximum intensity of loading that the foundation will safely carry without the risk of shear failure of soil, irrespective of any settlement that may occur. This is the safe bearing capacity of soil, which does not take into consideration the settlement criteria. This is the safe bearing capacity. And what is allowable bearing capacity? The net intensity of loading at which the foundation does not undergo, the excessive settlements or the permissible settlements is known as the allowable bearing capacity. These are the two terms which are very important to understand. And then we discuss what are the different type of failures in soil, in which we discussed the journal shear failure, we discussed the local shear failure, we discussed the punching shear failure, and what are the different values for punching, local, and journal shear failure. We have already discussed. We also discussed what are the different criterions for determination of the bearing capacity. As I have told you right now, that what is safe bearing capacity and what is allowable bearing capacity. We need to understand that whenever we are talking about the shear failure criterion, it is the shear failure which occurs within the soil, but from the shear failure point of view, we do not want our soil to fail, and neither we want our soil to undergo excessive settlements. Now, out of the two, whichever the value is lesser will be taken as the bearing capacity of soils. And probably I must remind you that we are talking about the foundation which is located at a depth at which it does not get affected from the seasonal volume changes or the presence of any adjoining structure. So out of the two, shear failure criteria and the settlement criteria, whatever the lesser value of the bearing capacity, it has to be taken into consideration for the calculation of the different sections of columns or any other criteria while designing. Because so far you might have understood that if the calculations of the bearing capacity they are wrong, it is very difficult to say that whether your structure is going to be safe in future or not. So let us try to understand what are the different factors on which your bearing capacity depends. First is the nature of the soil, nature of the foundation, because if the soil is granular, or it may be clay soil as well, it is the clay, the cohesion factor which is predominant in clay, and the friction angle which is effective in introducing the shear resistance of the soils. So accordingly, it depends on the nature of the soil. The nature of the foundation means whether it is the isolated foundation, whether it is the combined footing or raft footing, and what is the size of the foundation, what is the L and B, length and breadth, what is the depth of the footing. All these factors, I mean, they affect the bearing capacity of the soils. Total and the differential settlements, they have to be within the permissible limits, as we discussed earlier. And you see the location of the groundwater table is again very, very effective. One of the parameters which affect the bearing capacity, because if the groundwater table is within the zone of the significant depth, I mean, significant depth is the depth of the soil which contributes towards taking the loads of the soil coming from above. If the groundwater is within that zone, uh, it will lower down the bearing capacity of the soil. We'll see in further analysis of Terzaghi and Prandtl or the Meyerhoff as to how the fluctuations in the groundwater table does affect your bearing capacity of the soil. And the initial stresses, you may must be remembering that we may have the over consolidated clays or the soils or the normally consolidated the soils, depending upon their historical background. It does affect the bearing capacity of the soils. Now there are 6 methods for determining the bearing capacity of soils. you know they are analytical methods, they are the field methods, they are the laboratory tests, including the penetration test. Now if we get in touch with the analytical approaches, the Silcher was the first one. He gave the theory that was based on the theory of elasticity, then Rankin's theory, Pocker, Bell, which is based on the classical earth pressure theories, then Fellinius and Prandtl and Terzaghi's method, Scampton, Meyerhoff, Hansen, and Bala advanced their theories based on the theory of plasticity. These are the tests, the methods, in addition to the field test, that is plate load test and the penetration test. Uh, then we also discuss what is the Rankin theory. Rankin gave us an idea as to how we can find out the depth of the foundation, though it is a very approximate method and very conservative to be used for the practical purposes. Already discussed with you that he considered the element 1 and element 2, one below the foundation and the second element just far from the vertical face of the foundation. And we have come up with this the final value, that if you try to analyze according to the major principal stress or minor principal stresses theory, the depth of foundation can be calculated according to, the df is equal to q upon gamma 1 minus sine phi upon 1 plus sine phi whole square. You'll be surprised to know that it does not take into consideration the size of the footing. You know, the in fact, when we discuss the bearing capacity, as I've told you earlier, that the size does affect the bearing capacity of the foundation. This Rankin's method was taken forward by Prandtl as well as the Terzaghi's theory for determining the ultimate bearing capacity of the soils. We'll listen right now. Now, Prandtl made an analysis of some of the soils. Prandtl analyzed the plastic failures in metals when punched by hard metal punchers. He advanced the theory in the year 1920 and 21. This analysis has been adopted to soil when loaded to shear failure by a relatively rigid foundation. So this was just the advancement of what Rankin has said. But let us see what are the assumptions in the Prandtl's theory. First is the soil is homogeneous, isotropic, and weightless. Homogeneous means that the material is same throughout. The strata we are discussing. In the isotropic means that all the properties of the material, they are same at all the places. And the second, Mohr-Coulomb equation for failure envelope, as we know, tau is equal to C plus sigma tan phi, is valid for the soil. The third one, wedges 1 and wedges 3 act as rigid bodies. The zones in sector 2 deform plastically. In the plastic zone, all radius vectors are planes through A and B are failure planes, and the curved boundary is a logarithmic spiral. Wedge 1 is elastically pushed down, tends to push the zone 3 upward and outward, which is resisted by the passive resistance of the soil in these zones. The stress in elastic zone 1 is transmitted hydrostatically in all the directions. Now you can understand what just now I have conveyed to you. This is the diagram, and this is the foundation of it B. This is the triangular portion, zone 1, zone 2, and zone 3. This is the logarithmic or the spiral boundaries. So zone 1, 2, and 3 needs to be analyzed And when we draw the Mohr circle for the different type of forces acting on the soil wedge, we come up with the equation like ultimate bearing capacity Q ultimate is equal to C cot phi into n phi dot e raised to power pi 10 phi minus 1. This Prandtl's equation, this one is for C phi soils. And if for purely cohesive soils, that means the friction angle is 0, Q ultimate gets reduced to 5.14 C. Now, this is how we can find out the bearing capacity of soil for C phi as well as cohesive soils using these equations being advanced by Prandtl. Now, if you take into, I mean, if you try to discuss what are the different points of Prandtl's theory, it is basically based on the assumption they have assumed compound rupture surface consisting of of a logarithmic spiral and the tangents to the spiral. It is developed from a smooth and long stiff footing. It is for the long stiff footing resting on the ground surface. The depth of foundation has totally been neglected by Prandtl, and Prandtl's compound rupture surface corresponds fairly well with the mode of failure along curvilinear rupture surfaces observed from the experiments. Now, Prandtl's expression as originally derived does not include the size of the footing. This is one of the limitations, that the size of the footing has totally been neglected by Prandtl's theory. Now, this theory of Prandtl's was being extended and improved by Terzaghi, who is also known as Dr. Terzaghi, the father of soil mechanics. Now, let's discuss what he says about this one, the bearing capacity of soils. Now, the assumptions he made is that the soil is semi-infinite, homogeneous, isotropic, weightless, and it follows the rigid plastic material. And he has done it for the shallow foundations. That means the depth of foundation is not greater than the width of the footing. That means it is for the shallow foundations. And the general shear failure just occurs in the soil. General shear failure, what I have in my recap, I have told you that this kind of failure happens in case of dense soil, where the relative density of the soil is around 70% or more than 70%. Base of the footing is rough. The soil above the footing can be replaced by a surcharge stress. This in fact means that the shearing resistance of the soil located above the base is neglected. These are some of the assumptions. Now, these are the failure surfaces. These are the failure surfaces. Now, the depth of the foundation has been denoted as df. And again, as what we have seen in Prandtl case, zone 1, 2, and 3, similarly, in Terzaghi's analysis, again, zone 1 is the triangular portion, which is a part of the foundation. This zone C, D, E, F, G can be divided into 3 zones. Zone 1 is a triangular portion. Zone 3, zone 2, 2 zones of radial shear BCD and ACG. They are the outer edges of the loaded strip with their boundaries making an angle of 45 minus 5 by 2 and 5 with the horizontal. And zone 3, these are the passive zones known as passive Rankine zones, AGF and BDE, with their boundaries making an angle of 45 degrees minus 5 by 2 with the horizontal. Now, if we try to analyze all these, the surfaces like this, if we try to resolve the forces, this is the triangular portion, what we have seen, and this is B is the width of the foundation, and let's try to resolve. Now, in this triangle, which is having the B as the width, if we take the cos of the angle, cos phi, phi is the angle here, cos phi, if we take cos phi and try to solve for CA, CA will be equal to B by 2 upon cos phi multiplied by C. And this, because all the force, the weight of the, this wedge triangular portion, it will be equal to gamma B square tan phi upon 4. and having CA and W calculated at our end, and the summation of all for the equilibrium purposes, the summation of all the vertical forces, it has to be 0. So we are left with B into Q ultimate plus gamma B square tan phi upon 4 minus 2 PP minus BC tan phi is equal to 0. And Q ultimate will be equal to, after solving this one, twice PP upon B plus C tan phi minus gamma B tan phi upon 4. Now this will treat it as equation for 1, 4, 1, 5 and 1, 6, which will be used subsequently in order to find out the ultimate and the final equation according to the Terzaghi's theory. Now, for the simpler cases of D is equal to 0 and C is equal to 0, PP can also be found out using this equation. Now, when we try to substitute those one in equation 1, 5 and 1, 4, like this, you get the value of n gamma equal to 0.5 k p gamma upon cos square phi minus 1. This n gamma value has to be used somewhere else. In the later I'll tell you when we find out the other parameters. The value of kpy is obtained by means of the spiral or the friction circle method. This is n gamma is called the bearing capacity factor, expressing the effect of the weight of the soil wedge ABC of a cohesionless soil. Now, these are the different, when we try to resolve for ppn, this is the equation what we get. And further, also the total passive earth force pp on the contact face is equal to ppn upon cos delta. And what is pp? If we try to consider the whole or all the vertical forces acting and try to resolve, we get an equation like this. Now Q ultimate will be C into kpc upon cos square phi plus tan phi plus Q kpq cos square phi plus gamma b upon 4 tan phi into k p gamma divided by cos square phi minus 1. This is the equation 2, 3 after resolving all the forces. Now, these are the two, if a soil wedge ABC is assumed to be weightless as what has been assumed by Prandtl, so equation 21 gets reduced to CNC plus, Q is again gamma D, this is the surcharge load, and Q. On the other hand, if C is 0 and Q is 0, gamma being greater than 0, the bearing capacity is given by the equation 17 and 18, what I have explained to you earlier. So Q ultimate will be equal to 0.5 gamma B n gamma, all right? And this is in terms of kpy. And ultimately, when we try to resolve all the forces and try to calculate Q ultimate, it will have the three components. One is because of the cohesion, the other one is because of the surcharge load, and the third one is the depends on the dimensions of the footing and can be written as CNC plus gamma D NQ plus 0.5 gamma B N gamma. This is known as Terzaghi's general bearing capacity equation, which is based on the concept that your foundation is a strip footing and the failure is general shear failure. The coefficients of NC, NQ, N gamma, they are called the bearing capacity factors for shallow continuous footings. The different values of NC, NQ, N gamma we can have from the various tables, whether it is the the Terzaghi's theory. The different tables have been given. Now, bearing capacity of, as per the Terzaghi's theory, CNC plus gamma D NQ plus 0.5 B, 0.5 gamma B N gamma. I mean, it was for the C5 soils. Now, if only you have got, the cohesive soils where phi is 0, you get reduced to, Q ultimate is equal to 5.7 C. And for the stiff footing at a depth DF, when you take into consideration the surcharge load as well, so it will be 5.7 C plus gamma D. Now, this, what we have, as I have told you earlier, this was the concept for general shear failure. Now, if the conditions are for like local shear failure means the relative density of the soil is in between the the loose and the dense one. That means around 50% the relative density. Then you can Terzaghi conveyed that you can have the cohesion component which will be around 2/3 of actual C, and the phi value can be calculated from the relation tan phi dash is equal to 2/3 of tan phi. uh, this is how we can apply the Terzaghi's equation, which was originally for the general shear failure, into the local shear failure. Now, this is the diagram which gives you an idea that how we can have the values of NC, NQ, N gamma for the different values of phi, because they are the bearing capacity factors whose the values are totally dependent on the value of angle of internal friction. Just a quick note that as a general guideline, if failure occurs at less than 5% strain and if density index is greater than 70%, general shear failure may be assumed. And if the strain is between 10 to 20%, and if the density index is less than 20%, the local shear failure may be assumed. For intermediate situation, the punching shear failure, right? Now, these are the different values for NC and Q. N gamma, uh, uh, what I told you from the graph as well. Now, this theory has been, extended for the circular and the square footings as well. We'll see in the next lecture as to if you have the Terzaghi's theory with you and equation with you, CNC plus gamma d n cube plus 0.5 b 0.5 gamma b n gamma, which was originally being crafted for the stiff footings, shallow foundation, how this theory can be advanced to other type of footings like circular footing or the rectangular footings or different kind of footings. This we'll study in my next lecture. Till then, enjoy the lecture, stay safe, stay healthy. Thank you.